We're going to continue with complex analysis. We did complex analysis in a day, right? Now again, the difference between this and a legitimate class in complex analysis is proofs. And you're going over all the technical conditions. If you want to prove the Cauchy residue theorem, you eventually start off and say, if you have a function which is differentiable, and you integrate it on a nice, simple closed curve, you're going to get 0 because there's no poles inside. And you start working with stuff like this, and you start doing it on simple regions, maybe on squares, maybe on triangles. Triangles are very nice. They piece together, form very good objects. And you do the whole thing, and you build it all up. I am not going to bother doing that. We will just assume it can all be done. We will assume the Cauchy residue theorem is usable. If you haven't watched the lecture I've posted on Green's theorem in a day, if you do not remember that from Calc 3, I suggest you watch Green's theorem in a day. It will take you less than a day to watch that. It's about 50 minutes. It's a way of rigorously talking about how you do these path integrals, how you do these line integrals. That's really what's going on. That's why complex analysis works so nicely. I thought we would do an example. In the interest of boring as much as possible, as many of you as possible, I thought I would take an example that at least 2 people in the class know well. What example?
The Cauchy.
Yes, excellent. And you know why I'm doing it? No, I can write Cauchy twice. It's the all Cauchy lecture, right? So we can use Cauchy's name twice. So the density is f of x is 1 over pi 1 over 1 plus x squared. Now when you're looking at this, the most difficult part is the normalization constant. Why is it 1 over pi? Well, one thing is to know the antiderivative of 1 over 1 plus x squared. So what is the antiderivative of 1 over 1 plus x squared? Octan, right? And if you remember, if you have a of b of x equals x, so if a and b are inverse functions, then you get a prime b of x times b prime of x equals 1. This gives you b prime of x is 1 over a prime at b of x. And so here we would just take tangent arctangent. The tangent of the angle whose tangent is x. And you would draw your triangle here. If this is theta, if I want the tangent of theta to be x, I would choose a triangle like this. And you can go through the algebra and you'll see that the derivative of arctangent is just 1 over 1 plus x squared. I'll post a complete calculation of that in the additional comments for today. But this is a really nice use of the inverse relation law. You might have seen this if you know the derivative of the exponential function, you can get the derivative of the natural logarithm. You use the exponential of the natural log of x is x, and you move on like that. So this is an extremely useful relationship to know. If you know one derivative, you know the other. So now the integral from minus infinity to infinity of 1 over 1 plus x squared dx is equal to the arctangent of infinity minus the arctangent of negative infinity. So it's pi halves minus negative pi halves is pi. If you're a little bit uncomfortable with putting in the infinities, just take the limit going from minus r to r, going like that. OK, looking at this, before you saw the calculation, let's assume you forgot about arctangent. Are you surprised to see a pi coming into play? I'm a little surprised. Maybe I could say, well, it kind of looks like 1 over x squared. That's maybe like 1 over n squared. That goes to pi squared over 6. That's a real stretch, and I'm only saying this because the colloquium today is Shannon talking about the sum of 1 over n squared. Right? The pi should look quite mysterious at this point. I want to show you a way where the pi is going to come in a very natural way, the Cauchy residue approach. So step 1 in all of these things is you need to figure out what should your function be as a complex variable. For the most part, this is essentially the substitution game. Right? Essentially, it's a global search and replace. Every time you see the letter x, so long as it's not like exp for the exponential function, replace it with the letter z. And you get 1 over 1 plus z squared. Have we seen this function before? 1 over 1 plus z squared. I'll rephrase. Where have we seen this function before? We did see it. We saw it when we were trying to understand what concept. Poles. When we were trying to understand poles and residues. It was not a coincidence I chose to look at that function then. This was putting something in the bank. We saw we could write this as 1 over z minus I, 1 over z plus I. So there's going to be two poles at I and at minus I. And then we saw how to calculate the residue. So near z equals I, we would write z plus I as z minus I plus 2I. We did the geometric series expansion. We figured out how to handle what was going on. So the integral we're trying to do, we'll go from minus r to r, and we'll try to integrate our function. Our function has a pole here at I and a pole here at minus I. And what we're going to do is we're going to do a contour like this. So one of the hardest parts in all these problems is figuring out what contour to choose. Usually you choose like a circular arc or you choose a rectangle. These are the two most natural things to try. What's nice is if we integrate the function along the real axis, we get the integral we care about. And then the hope is that we have decay over the arc, so that in the limit as r goes to infinity, the contribution from that piece becomes 0. And in the Cauchy residue formula, we'll say the integral over the whole thing is equal to 2 pi I times the sum of the residues. So we get 1 over 2 pi I, the integral over the closed contour, we'll call it gamma, of f of z dz will equal 1 over 2 pi I, the integral from minus r to r, 1 over 1 plus x squared dx, plus 1 over 2 pi I, the integral, we'll call it gamma sub r, of 1 over 1 plus z squared dz. I just realized I have a mistake in my notes, but fortunately you haven't seen my notes and it's not fatal. This is equal to the sum of the residues inside. So where is the only point where we have a residue inside? What's the value? I. So it's f at I, and we showed last time it was equal to 1 over 2I. What's nice is there's a general theorem. If you have f of z is 1 over z minus I times g of z, where g of z is holomorphic and not 0, then the residue, or in fact, can even be 0, the residue is just the value of that at the point you care about. And the idea is we're taking the limit as z goes to I, and we want to look at what is the coefficient of the 1 over z minus I term. That's going to be the constant term here. So you just substitute z, you substitute I for z. All right, so we just have the residue is 1 over 2I. You should be happy at this point. This should be going to 0. This should be negligible. This is a real number. We're dividing by 2 pi I. That's a little scary that we're dividing by an I, but this has an I down below. The i's will cancel, and we'll get a real number. We've got a pi over there. Oh, and the 2's are going to cancel as well. Great. It's going to just be pi. So the algebra, if we can show that this is 0, then the integral we care about is pi. So if the integral over gamma r equals 0, then the integral from minus infinity to infinity of 1 over 1 plus x squared dx equals pi. And that's going to just come from then taking the limit as r goes to infinity. So all we have to do is show that this integral tends to 0. Is the integrand large or small as r goes to infinity? What do you think? I'm sorry, small. Can you quantify how small it is? How small is 1 plus z squared? So you can tell me approximately what it is. It's approximately 1 over z squared. So it's and we're on a circular arc. Right? This is a circle of radius r. So it's approximately 1 over r squared. This is a tough lecture as a Bostonian. Right? It's approximately 1 over r squared. But we've got to be careful. We have 1 plus z squared. Can you give me a bound that will always work for that?
1 over r squared minus 1.
Excellent. So we can use 1 over z squared plus 1 in absolute value is strictly less than or equal to 1 over r squared minus 1. And the reason this is true is the worst possible case is if z squared is real and equals a negative number. Is that case going to happen for us? Well, yeah, it could actually happen right up here at the very top. At the point IR, we'll get negative r squared. That's the worst case. Any other case, we're not going to get as much cancellation. So now, the length of gamma of r. What is the length of that curve? So how long is that top arc? Pi r. So therefore, the contribution of the gamma r integral is less than or equal to 1 over 2 pi times the maximum value, 1 over r squared minus 1 times pi r. Well, this is basically, the pi's cancel. I can even throw away the 2. I don't care about the 2. It's r over r squared minus 1. This goes to 0. So what was nice is we didn't need the full strength of the decay here. We didn't need that it was 1 over r squared. We just needed that it was something that was a little bit better than r. And so now the contribution of this piece is 0, so this piece equals that piece, and there we go. I find this is a lot easier than the arctangent. If you doubt it, I'm not going to do the calculation now. What should we replace 2 with? So we could do 3. 3 is a bit of a challenge, because if we do 3, we've got to be careful, because now if we integrate 1 over 1 plus x cubed, when x is negative, you're actually going to have 0 in the denominator. You would have to integrate from 0 to... So you should replace 2 with 4. Or actually, this year works, 2014 works, 2000 works. Replace it with a nice big even number. Does anybody know the antiderivative of 1 over 1 plus x to the 4th? No. But if I replace, if I replace the 2 with the 4, can we figure it out? Yeah. In fact, I know 2 people in this class have had to figure it out. Right? Did we do contour integration for this when you were doing small? Okay. So this is a powerful, powerful way to use the Cauchy formula. All we have to do then is figure out where the zeros are. The zeros are going to be nice, the poles of the function, or the zeros of 1 plus z to the 2014 whatever. And then it's just simple algebra. It's just find the residues and then do some algebra to simplify at the end of the day. So the higher your degree is here, the more complicated it's going to be, the more zeros you have in play. All right. There's a lot of examples we could do about actually applying the Cauchy residue formula. Yes?
Would you be able to explain really quickly how you get from like b prime of x equals that to arctan prime of x equals that?
Sure. I'll go through that calculation. It's a fun calculation. So again, there's a lot more we could do with contour integration. This is not a class in complex analysis. I just wanted you to have some idea of how to do this. If you want to do some problems for homework, I will make them optional, and I'll just have them as like extra credit homework problems. Okay? And you can just let me know, and I'll give you some of my favorites. This is probably, if there's time, I will mention my favorite one. All right, so let's go to the question how we get the formula for arctangent. So we know the tangent of arctangent of x equals x. The tangent of the angle whose tangent is x. So if we take derivatives, we get tangent prime of arctangent of x times arctangent prime of x equals 1. This is just chain rule. So we get arctangent prime of x is 1 over tangent prime of arctangent of x. Now we have to recall, what is the derivative of tangent? How do you calculate the derivative of tangent?
You know it. You recall it as secant squared.
How do you, oh no, unfortunately you forgot that. How do you calculate the derivative of tangent?
Sine over cosine.
Sine over cosine, use the quotient rule, right? The derivative of sine over cosine, use the quotient rule, you get tangent prime of u is, it's going to be a cosine squared, so it's going to be a secant squared. So it's 1 over cosine squared, it's secant squared of u. So we get arctangent prime of x, well 1 over secant squared, secant is 1 over cosine, so we get cosine squared of arctangent of x. And now we draw our picture. I want the angle whose tangent is x. I make this side x, this side 1. This is the square root of 1 plus x squared. So the cosine of theta is 1 over square root of 1 plus x squared. So now when we square it, we get 1 over 1 plus x squared. And if you want, you can try to figure out, is there a nice antiderivative for 1 over 1 minus x squared? Does something, when do you have something nice for stuff like this? So these are fun formulas. It's a really nice use of the chain rule. Okay. Any other questions about these contours and doing stuff like this? All right. So what I want to do now is I want to talk a little bit about the proof of the prime number theorem. All right. I have no notes on this because I have done this so many times. I should know it by heart at this point. So we started off with the Riemann zeta function. And we had the Riemann zeta function initially only when the real part of s was greater than 1. We then talked about how to analytically continue this to a nice function for all s. It has a simple pole of residue 1 at s equals 1. Other than that, it's nice. The zeros of this function turn out to play a huge role in what goes on. Now again, this is a very blitzkrieg course in complex analysis. Logarithms play a huge role. There are two ways to write the zeta function. It's a sum over positive integers, and it's a product over primes. Which do you think number theory cares more about? Product over primes. The primes are our building blocks. Complex analysis loves integrating logarithmic derivatives. You integrate f prime over f, and we saw that this just gives you the order of the zero of the pole. And this is from, f of z is, an z to the n plus dot dot dot. I'll just do, it's centered at 0. F prime of z is n, an, z to the n minus 1. If you look at f prime of z over f of z, expanding about 0, we'll get n, an, z to the n minus 1. I can then pull this out, and I'll get 1 plus something involving z. Down below, I pull out an z to the n, and I get 1 plus something else involving z. So when z is very close to 0, the denominator looks like an z to the n, the numerator looks like n an z to the n minus 1. The an's cancel. The z to the n minus 1 cancels with that, and I'm left with n over z, 1 plus something like this when you do all the algebra out. And so now if I do an integral of this, we know the integral of a sum is the sum of the integrals, and I'm going to just get n if I integrate along, in fact, a circle, or in fact, any closed curve containing the origin. And this is why complex analysis loves logarithmic derivatives. And this is just the derivative of the log of f of z. Now, unfortunately, the logarithm is a complicated function in complex analysis because you can't go all the way around if you want to do the log of z. Glossing over lots of stuff right now. But this should explain to you why we care about logarithms. We have two ways of writing the Riemann zeta function, as a sum or as a product. I always tell you we want to use logarithms to convert sums to products. Well, we've already got a sum, right? Is there any need to convert the product to a sum if we already have a sum? No. But Complex analysis wants us to take the derivative of the logarithm. We don't want to take the logarithm of the sum and then differentiate that. We want to use the Euler product. Take the logarithm of that, convert that to a sum, and then integrate that term by term. So this is going to be the quick proof of the prime number theorem. It's not going to prove it in full detail. It's going to reduce it to knowing some things about the location of the zeros of the Riemann zeta function. So the prime number theorem was conjectured in the 1800s. Chebyshev had some really good progress towards it in around the 1850s. It was finally proved in the 1890s, 1896, independently by Hadamard and de Villers-Poisson. That's the best I can do in terms of pronouncing the name. And it was, not surprisingly, heavily using complex analysis. This bothered a lot of people because if you think about counting numbers, you should not have to resort to the complex plane to count sets of integers. And so there was a thought that there should be an elementary proof of the prime number theorem, and no one could find it. So eventually people figured out, okay, there probably isn't an elementary proof, and if there is, it's going to tell us an enormous amount. Both statements are false. There is an elementary proof, it tells us much less. It shouldn't be too surprising in some sense that it tells us less, because when we use complex analysis, we're throwing a lot of heavy machinery at the problem. If you think back to, how many of you have seen Newton's method? You use tangent lines to approximate a function to find roots. Newton's method works a lot better than divide and conquer. Divide and conquer, every time you apply, you have your error. It takes 10 iterations to get another 3 digits. Every time you use Newton's method, you double your decimal digits. The reason Newton's method destroys divide and conquer is because Newton's method uses more. It uses the differentiability of the function to approximate it very well. If you've taken probability, think of the central limit theorem versus Chebyshev's theorem. The more information you know about a system, not surprisingly, the more you can claim. So when we use complex analysis, we're not going to just prove the main term of the prime number theorem. We're going to get some control over the error term. All right, so complex analysis, zeros of zeta of s, and the prime number theorem. All right, so we have all of these together. So zeta of s is the product over primes 1 minus p to the minus s inverse. Let's say the real part of s equals c is greater than 1. Why am I assuming the real part of s is greater than 1? Yeah, I want things to converge. Right? Having things exist, having things converge, that's a really good start. Okay? So we will choose the real part of s to be greater than 1 so that everything makes sense. The goal will then be to shift contours. This is essentially the biggest trick we know. You take an integral over a line that you care about and you show it's equivalent to other integrals. All right, well, let's look at the logarithm. So the log of zeta of s is going to be the sum over primes. We'll get a negative 1 coming out, and we'll get the log of 1 minus p to the minus s. Now we take the derivative, and we get zeta prime of s over zeta of s. So we're taking the derivative. What's the derivative of a sum? Right, so we pretend we've justified that. We have minus the sum over p. Now we have to take the derivative of log. So we get whatever we had inside comes in as our denominator. Now we have to take the derivative of this piece with respect to s. Note that p to the minus s is e to the negative s log p. Remember, we hate things in bases other than e. So if I take the derivative of this with respect to s, I'm just going to get negative log p times itself. So I have, when I take the derivative, I have a negative from this and a negative from this. The two negatives cancel, and we'll get log p times p to the minus s. When you look at this, what should you be thinking about this expression? I'm sorry? The problem is they all have very different weights. And so if we took this and put this inside as an exponent, it's not a bad idea to try, but it would, the exponents would become horrible, and we actually prefer sums to products.
It's pretty much just the sum of log p. But
Well, log p times p to the minus s,
the denominator is pretty close to that.
depending on the value of s.
Oh, yeah, no,
And that's the problem. The sum of the reciprocals of the primes diverges, and we can prove that elementarily. We have a 1 over 1 minus p to the minus s. As a Bostonian, it pains me to do this, but what if I write p to the minus s as r? Would a rose by any other name guide you in how to do mathematics? If I write it like this, that was the original version of the Shakespearean quote. If I write it like this, does that give you a better sense of what we should do? Geometric series. When you see expressions like this, you need to be automatically thinking something like that. You should be thinking, oh, this looks like a geometric series where the ratio is p to the minus s. If we do that, we now get minus the sum over p, the sum over k, log of p times p to the minus ks. Now the difficulty is if s equals 1, this blows up. But if s is a little bit greater than a half, I can take k equals 2, and I'll have something greater than 1, and everything is fine. So really, the difficulty, if I want to go all the way down to 1/2, is just the k equals 1 term. So I should really break this up into two things. Minus the sum over p, the k equals 1 term, the log p over p to the s, plus what I'll call good of s. And I will not worry about good of s anymore. This is the k greater than or equal to 2 piece. In a real class on complex analysis, you would prove this rigorously and you would handle this piece. But this piece is not going to be bad. Things are going to be converging nicely. We're not going to be worried about this. The 1 over p, that piece is going to matter. All right, and so this is the zeta prime over zeta. All right, so it turns out that it's useful to give this a name. So this is the same as the sum over all integers n of lambda of n over n to the s plus good of s. So we're introducing this new function. Lambda of n is the log of p if p is n to the k and 0 other. And in fact, if I do it like this, it's exact. There's no error at all. So when you look at the sum should clearly the sum should clearly only exist when n is a power of a prime. We have a log of p over p to the s. The only terms that survive are when we have a power of a prime. If you look at what's going on, we have p squared, p cubed, p to the 4th, p to the 5th. Oh, I'm sorry, it's not p equals n to the k. It's n equals p to the k. So the only terms that survive is when our n is p to the k. So we can just introduce a new function. This is exact. It turns out that it's easier to study the primes with weights, and in fact it's easier to study not just the primes, but a little bit more than just the primes, the prime powers. We showed early in the semester that the prime powers are insignificant. Without too much work, you can bound that the number of prime powers up to x is bounded by square root of x. The number of primes is on the order of x over log x. There are so few primes that are, prime squares, prime cubes, prime to the 4ths, that if you include them in your counting, it doesn't make any real difference. And in fact, the inclusion from them is going to be even lower than the error terms we get under the Riemann hypothesis. It's not going to matter. It just makes the life a lot easier to work with something like this. So if you want, you can drop the good of s, or you could work with this function and deal with prime powers. You can do various inclusion-exclusion games to get rid of the prime powers. These are all things analytic number theorists love to do. You have lots of different choices as to how you proceed. Okay. So now that we have this, now let's get some dividends of complex analysis. So we're going to start, we will integrate from real part of s equals c, zeta prime of s over zeta of s, x to the s over s ds. This is negative the integral real part of s equals c, lambda of n over n to the s, x to the s over s ds. Okay, so in terms of doing the integral like this, we've multiplied it. We've multiplied it by a x to the s over s. Can we multiply by whatever we want when we do our integration? Can I just put in an x to the s over s? I did it on both sides, right? As long as you do things equally on both sides, it's fine. This leads to the theory of test functions. And so if we get to zeros of L functions later in the semester, we will see this concept again of a test function. So rather than integrating the function I care about, it's sometimes convenient to hit it with something nice. And that will lead to cleaner integrals, more pleasant integrals. Why is this a good thing to look at? Well, when I do the calculations over here, if I didn't have this, what I would get over here is if I had a completed contour, I would get contributions from the zeros and the poles of zeta prime. What this is going to do is that's going to weight the contributions by this fact of x to the s over s. So there's two possibilities now. And so I'm going to just sketch really what's going on. 0, 1/2, 1, here's c. We're going to look at a contour like this. So maybe we'll go from c minus it to c plus it, and over here this might be minus r, where r is some big number. And as we do this integration on this side, the Cauchy theorem tells us that if we multiply by 1 over 2 pi I, so let's just put in a 1 over 2 pi I, doesn't make a difference, then this is going to be just a sum of the zeros and the poles times the residue. The residue is now going to have an x to the s over s. What you see is the zeros and the poles with larger real part will contribute more. There is one there's one pole at s equals -1. When you have a pole, remember we looked at the logarithm, if we didn't have this x to the s over s, it would contribute -1. Because there's a pole, it would contribute -1. So I will move this negative sign over to here. So now the pole is going to contribute the residue, and the residue is going to just be x to the 1 over 1. Okay? This is the main idea. The pole at the zeta function gives us an x. And then every other zero is going to give us an x to the rho over rho. Except what's the one point that we have to be careful about? We have the zeros and the poles from the zeta function. What else do we have to be careful about? S equals 0. So fortunately, s equals 0 is not bad. What's going on with the zeta function will cancel out with what's going on here. And so this piece is going to contribute x. And then because we have the minus sign, now all the contributions over the zeros is going to be a negative. And we'll have a sum over rho of x to the rho over rho. This sum, unfortunately, does not converge absolutely. But if you pair the zeros with complex conjugates, because the zeros occur in complex conjugate pairs, if you have a 0 over here, then the complex conjugate down here is also a 0. If you pair them like that, this sum does converge. And since we're doing things in a finite box, we can always make that work. Then what you would need to do is you would need to know enough about the Riemann zeta function that you can understand what's going on those three sides and say that that's negligible in the limit. And so the left-hand side is going to give us this contribution. Okay. Any questions about the left-hand side? Now we have to calculate the right-hand side. How do you think we should start? Oh, oops, I'm missing something. How do you think we should start? Interchange, right? This is the same as the sum over n of lambda of n, the integral 1 over 2 pi I, x divided by n to the s over s ds, real part of s equals c, which is greater than 1. This turns out to be an incredibly nice integral. So the integral is 1 if n is less than x, 0 if n is greater than x. If it equals x, I believe it's 1/2. What can we do to make sure we never have to worry about that catastrophe? Clearly, if x equals n, the integral is a little bit different because we're integrating 1 over s. What could we do to make sure we never have to worry about the case when x equals n? What could we do to make sure we never have to worry? What are we choosing right now? What's our free parameter? So the zeta function is fixed, but we get the freedom of choosing x. So when we make the choice for x, what do we just have to be careful about? Don't choose an integer. Actually, we can choose x to be certain integers. Don't choose x to be a prime power. If you always make x be half an integer or something like that, you're fine. All right? Let's just assume that the integral is as claimed. If the integral is as claimed, then when n is less than x, I get 1. When n is greater than x, we get 0. And so this would give us the sum over all n less than or equal to x of lambda of n, which is basically the sum of all prime less than or equal to x of log of p plus something much smaller. And so now look at what's going on. The sum of log p up to x is x minus the sum over zeros. The Riemann hypothesis says that all the zeros are either negative even integers or they have real part 1/2. The negative even integers is coming from the functional equation of the Riemann zeta function. Imagine all the zeros have real part 1/2. And that means all the zeros lie on this line. That means all the things over here look like x to the 1/2. And then this would tell us we expect this sum to be of size x. So let's just talk a little bit about heuristics as to what this would entail. So now we have the sum p less than or equal to x of log of p is like x plus something of size x to the 1/2, if we assume the Riemann hypothesis. Well, if I want to look at the sum of log p, the log of p is approximately about how big do you think log p is as we go through this range? About log x. I mean, if you want, look at all the primes going from square root of x to x. Look at all the primes going from x over log x to x. This is all approximately log x. So you get log of x times the sum p less than or equal to x of 1 is approximately x. So you get the sum p less than or equal to x of 1, which is pi of x, the number of primes at most x, is about x over log x. And there's the prime number theorem. And in fact, not only do you get the prime number theorem, you get an error term coming from the zeros of the Riemann zeta function. The error term is actually going to be a little bit larger than square root of x because of what's going on. This is just a quick rough heuristic. It turns out if s is a 0 of the Riemann zeta function, the functional equation gives you that 1 minus s is also a 0. So when we're looking over here, if we had a 0 off the critical line over here, we would have a corresponding distance off over here. So the best we can do in terms of where the zeros are would be as if they all have real part 1/2. If there's something with a smaller real part, you might think, hey, that's helping us over here. But it then has a corresponding sibling over here that would be worse for us. So the Riemann hypothesis is telling us the zeros are as nice as possible. So all it comes down to now is showing that this integral equals 1, showing that we can move the contours as we want, and getting some idea of where the zeros are of the Riemann zeta function. And so unfortunately, we don't have good knowledge of where the zeros of the Riemann zeta function are. In Friday's class, I will give you a proof that there are no zeros on the critical line, on the edge of the critical strip with real part of s equals 1. Let's quickly talk about this integral in the few moments we have left. All right, so let's assume x is greater than 1. We want to integrate x to the s over s ds. Real part of s equals c is greater than 1. So we want to figure out what's going on. So let's write s as c plus it. So this is the same as the integral t goes from minus infinity to infinity of x to the c plus it over c plus it dt is I dt. Well, x is a number that is greater than 1, so we are assuming that n is less than, okay, so that's equivalent to the case over there. Okay, so here's what's happening. Here's c, here's 1, here's 0. Let's take a closed box like this. When you look at this function, where's the one place where this function has a pole? Where does x to the s over s have a pole?
0.
At 0. And the residue is going to just be 1. Over here, we're going to go up to some big value of t. So let's have this as c plus it, c minus it. We'll have a negative r over here. As we do the integral over here, notice that s is going to be large. S is going to be at least the absolute value of t in size, because we're that high up. And now over here on this piece, if we do the closed integral, well, if we integrate x, now it's c that changes. The t is fixed. So on this piece, it's going to look like the integral of e to the negative c, e to the negative c log x divided by t in absolute value, dc. And c is going to go from, the notation is becoming a nightmare. We'll have c go from c naught to minus infinity. That is completely irreadable. All right. What's going on here? We integrate c, so I'll use another variable. We have e to the u log x over t in absolute value du. U is going from c to minus infinity. We have an exponential integral. Now, when u is positive, there is a contribution here. But u is going all the way off to minus infinity, so this integral is going to be finite. We get to divide by the absolute value of s by t. So the integral over the top piece is going to be negligible. Similarly, the integral over the bottom piece is going to be negligible. And now we have to do, what about the integral over this piece? Well, on this piece, we have x to the negative r. The real part is hugely negative. Since x is greater than 1, this is going to be an extremely small thing. And so when we integrate 1 over s, that's going to bound by the length of the thing over here. So you just have to carefully go through and show that the contribution over these three pieces is small. This is how all these proofs go. All of these proofs go by showing 3 out of the 4, 2 out of 3, something like that. N minus 1 out of n pieces are negligible. And then the one piece that matters, the piece that you want, is then going to be the sum of the residues. Well, the only residue we have is we have a residue at 0 of 1. And there's our integral. What if x was less than 1? Would this argument still work? What would we do if x was less than 1? Would this argument work, or would something break down?
Left side.
Yeah, now we have something that's less than 1 to a negative power. So think of it as we have 1/2 to the negative r. That's the same as 2 to the r. We now have something that's enormous. So now, unfortunately, the contribution over this piece is not tending to 0. Now, we claim that the integral is 0, so we're going to have now massive cancellation. Massive cancellation is a very dangerous thing to look for. All right? You want to avoid massive cancellation. What do? We want to evaluate this integral, and if we try to complete the contour like this, we now have massive values on this side. So we can't complete the contour like this.
Look at it in the other direction.
Yeah, look at it in the other direction, right? If going that way doesn't work, try going the other direction. Well, what happens if we go the other direction? Well, we now have a number less than 1, and we're taking it to a larger and larger power. Oh, that's exactly what we want to do. Fortunately, frequently in life, there's only a finite number of options, and the finite number is a very small finite number. So here we only have 2 possibilities. Complete it in this direction, complete it in that direction. If one doesn't work, try the other. Okay? This is a quick sketch of the prime number theorem. And again, to make this rigorous, we now need to know where the zeros are of the Riemann zeta function. If you have zeros on the line real part of s equals 1, that's going to be very bad. Those will be contributing at the same level as the pole, and they could completely wipe out its contribution. Did we prove in a homework problem that the zeta function is not 0 on the line? No. We proved any amount to the right, any amount where the real part of s is greater than 1, we proved in that region that the zeta function does not vanish. We do not know about whether or not it vanishes on the line real part of s equals 1. It turns out if you can just show that it's not 0 on the real part of s equals 1, you have the prime number theorem. Your error term sucks, but you have the prime number theorem. So tomorrow's lecture is basically going to be, how can we replace less than or equal to, how can we replace greater than with greater than or equal to? And we'll use a wonderful trick by Mertens. So again, this is not a fully rigorous proof of the prime number theorem. I completely understand it's not. I want to get you to the point where if you want to read a rigorous proof now, you can now go and you can now read those resources. And you have the key brushstrokes, you have the main ideas. Okay.